Let's start with the theory in the first part. So the feedback control loop is a key component of every industrial process control system. It consists of composed of four parts, that is a process, a measurement, a controller, and a final control element. Flow of information offers a way of control, then allowing for the effective use of raw resources and energy. Closed loop control occurs when all of these parts are coupled and information may be sent constantly through the loop. So the loop control occurs when the loop is stopped for any reason. For as when the control is set to manual control. So for the additional theory, the process of maintaining a specified amount of liquid within a container or vessel is known as liquid level control. So this is usually accomplished with the use of level sensors or probes offer input on the current liquid level. A control system can use this feedback to operate valve, pump, and other devices to change the flow of liquid into the container. So the flow control, on the other hand, is concerned with controlling the rate of liquid flow inside a system. Flow sensors and meters are used to detect flow rate, which is then utilized to modify valve, pumps, and other flow control equipment.
Assalamualaikum warahmatullahi wabarakatuh. My name is Mohammad Rafie bin Bahrin. My metric number is DD200115, and I will continue the experiment video, and I will talk about the procedure for this experiment. So the first step is to turn on the computer and run the process motion software in the computer. For the first task, at the screen, click online, click the level control or process button, and select the PID controller from the dialog box and enter the input for set point 120, KC5, TI 100,000, TD0, and MO0. And click run and run the system until it reach steady state. Make sure the valve A is in closed condition and valve B is in open condition. Valve C should remain closed throughout. After that, record the system output H and controller output M in the table. For the second task, repeat the procedure in task 1, but change the set point to 108 and click run and run the system until it reach steady state. For this task, make sure the valve A in open condition, meanwhile valve B is in closed condition, and valve C should remain closed throughout. Record the system output H and the controller output M in the table. For the third task, at the dialog box, remain the set point at 108, but change the KC to 100, and then click run and run the system until it reach steady state. For this task, make sure the valve A is in open condition, meanwhile valve B is in closed condition, and valve C also in closed condition. Record the system output H and controller output M in the table. For the fourth task, maintain all the value in the dialog box, but change the condition of valve A in open condition and valve B in open condition. Meanwhile, valve C should remain closed throughout. And then click run and run the system until it reach steady state. After a while, record the system output H and the controller output M in the table. For the fifth task, at 108 set point, change the KC value in the dialog box at 1 and click run and run the system until it reach steady state. In this task, make sure the valve A and valve B is in open condition, meanwhile valve C in closed condition. And after a while, record the system output H in and controller output M in the table. And for the last task, at set point 108, change the value of KC in the dialog box to 10 and run the system until it reaches steady state. In this task, make sure both valve A and B is open condition, meanwhile valve C in closed condition. After a while, record the value of H and M in the table. That's all from me for the procedure. Thank you.
Hi, my name is Michelle and today I will present the observation of this experiment. For the observation we get, a control system is analyzed based on the graph obtained after running the system with specific parameter. The set point was set to 120, while the value of KC, TI, TD and MO are 500,000, 0 and 0 respectively. Valve A is closed, while valve B is open, and the valve C remain closed throughout the process. After 85 seconds, the system reached an steady state and the corresponding value from the graph are recorded. The error is found to be a 16 and the controller output is 75 M and the total response time is 35. By dividing the error by the reference value and multiply by 100, the result for column 7 is calculated as 14.81. The initial reference value remains constant at 108 and subsequent experiments are conducted with a step charge of 30% in the reference value. The error, controller output, and the total response time and the column 7 value are recorded for each experiment. This process is repeated until it was reaching a reference value of negative 40%. Thank you, and I will pass to the next presenter.
Assalamualaikum. I'm going to present about the conclusion. The result obtained lead to the conclusion that the derivative time value can have both positive and negative effects on level and flow control. This is due to the fact that a process variable with a higher number of derivative times may perform poorly when used to control flow while performing well when used to control level. The amount of oscillation visible in the data can be used to gauge how well the process variable is working. Furthermore, as the derivative time is for the prediction horizon, an increase in derivative time can make the level and flow control respond quickly if the set point and load change. Moreover, when the derivative time grew, PID flow control show an active oscillation. This is because the flow control loop has a short time constant and acts quickly. As a result of the low-acting control loops, larger time constant, PID level control produce the least amount of oscillation. Therefore, PID flow control is quicker than PID level control in that it takes 1 to 2 minutes for the process variable to reach the set point. To achieve a good conclusion for the study, a number of recommendations may be made, such as tweaking the PID controller to improve the performance of the process variable for the level and flow control. This is because many complex processes can benefit from the use of a properly tuned PID controller. There are various tuning techniques, including the Cohen-Kuhn and Ziegler-Nichols tuning techniques. The reading of a process variable can then be improved by calibrating devices like flow transmitter and level transmitters. To make sure a instruments readings are consistent, calibration is frequently performed. That's all from us. Thank you.